Good morning. Good morning, everybody. So let me just wait till a lot of people join in. So there is quite less so far. So I will start once it's 11:30. Okay, so it's 11:30 now. So let me start. There are still a lot more people expected, but let's just go with this. All right. So today we will just continue from where we left off yesterday. So if you present my screen. Okay, so I hope you can see my screen. Yes.
Yes, sir.
All right. So thank you. So yesterday we were talking about basically derived distribution, right? And what we did was we began with the single variable case. Okay. We looked at first. We started with the like linear case, which is like y is equal to ax plus b. We looked at a greater than 0 and a less than 0. Then we found out that when we do this, we found out that fy of y is equal to fx of y minus b by a. Okay. Then there is a factor of 1 over a and with a modulus. Okay, this is the absolute value of a. So this was what we saw yesterday, and then we also did one more step. So what we did was suppose y is equal to g of x. Okay, so small y is equal to g of x, just like capital Y is equal to ax plus b. So similarly, yeah, so some y is equal to g of x, or if you, so this is monotone. Okay, then since it is monotone, you also have that h is equal to x, sorry, x is equal to h of y. Okay, and then what we showed yesterday was that fy of small y is equal to fx of h of y into h prime of y. Okay, so this is what we saw. So this was for the single variable case. So are there any questions in this part of what we did yesterday? Okay. So since I don't hear anything, I'm assuming everything is okay.
So, is it necessary that A should be less than B?
I'm sorry, I meant to say a greater than 0 as well as a less than 0. Two cases we saw, right?
Yes,
But
sir.
yeah, it was just a mistake. Is this clear? I hope I didn't confuse
Yes,
you.
sir. Yes.
Yeah. So there is no relation between A and B. There is nothing. All right. Okay. So secondly, now from this, what we want to do is we would like to generalize this. So we come to the multivariate case. Okay. So somebody has any question? So in the multivariate case, what we did is we looked at the same pattern. So what you have is basically uh, y. So basically y is some function of x. So y1 is equal to g of g1 of x1 to xn. Similarly, you have yn is equal to g of gn of x1 to xn, okay, then x1 is equal to h1 of y1 to yn, okay, xn is equal to hn of y1 to yn. So we have basically something like this. I will tell what is the equivalent thing. So there is no monotone in a multivariate case, right? So there is no meaning of like monotone functions, okay? Because there are n variables and n functions, and so there is nothing like monotone. But I will define what is an equivalent concept, okay? That we will come to. But suppose you have basically a function of x, and such that this inverse also exists simultaneously. Okay, we will look at some examples. You'll get this much clearer. But for now, you assume that you can go from y to g uniquely, and you can go from x to y uniquely. Okay. So now, what we know is that x is distributed as, okay. So there is some joint distribution for x. Okay. So now, just by looking at this formula, if you have understood this formula, arriving at the multivariate case is not difficult. Okay, so what you can do is that you can basically just look at the same expression and you will get the answer. So what is that? Fy1 y2 yn, y1 to yn. So this is very analogous to that. So you have x1 to xn. Okay, now you need to have functions in terms of y. So every x you are going to replace the equivalent functional form. So that will be h1 of. So I will write this as a y bar to indicate y1 to yn with an arrow. Okay, just to make my life little easier. Like this. Okay, this is nothing but y1 to yn. Okay. Now like this you have, and then you have here what is called as determinant of absolute value of determinant of Jacobian, okay, Jacobian matrix. So I will tell you what's a Jacobian matrix. Jacobian matrix of H. Okay, so what is the thing that you have? So this is analogous to taking the derivative in the multivariable case. Okay, you are taking the derivative of H here, right? So that is what this indicates. And what are you taking the derivative with respect to? That is with respect to y. Okay, so this is this. Okay, so let me just define what is J. So J is a n cross n matrix. JH of y is a n cross n matrix, which is partial derivative matrix basically. Okay, so this will be JH1. So H1 is, remember, H1 is a function of y. So this will be with respect to y1. All the derivatives of H1 first. Then you will do the same for H2. Sorry, it will be H1 only. All the derivatives of H2 with respect to y1 to yn. Similarly, hn, yn. Okay, so this is the Jacobian matrix. So you are basically, you see, what was the derivative before has become this. Okay, and if you interchange the partial derivatives, instead of writing like this, if you write it in the other way, if you write its transpose, it doesn't matter, because determinant of a matrix and its transpose is same. Okay, you know this. So because of that, even if you interchange how you write the Jacobian, it doesn't matter. Okay. So I hope this idea is clear. So let us look at few examples to make this more concrete. Okay. So remember, it is just not just the determinant. There is also the absolute value. That is something which very similar to how that is there in the single variable case. Okay. Any questions so far? Okay, so we will look at two examples, and then hopefully then we can wrap up this topic of derived distributions. Okay. So let's look at first the linear example. Okay, so let's take basically y1 and y2, and let's write it as some linear matrix. Okay, a11, a12, a21, a22 of x1, x2. Sorry, something happened here. X1, x2. What's happening? X1, x2 plus let's say b1, b2. Okay. So this is a linear case. So this you can write it as a compactly as y is equal to ax plus b. Okay. And further, let us assume that A is invertible, which means A inverse exists. So if you use the inversion, so we can get x is equal to A inverse of y minus b. So now let us assume that x, okay, is distributed as x is distributed as normal with mean 0. I'm taking an example of 0. In general, this may not be the case. And variance matrix, since it's a multivariate case, let's assume that the variance is sigma. Okay. So now what is the distribution of fx of x? So fx of x. So there are x's having x1, x2. So what is this? So this will be 1 over 2 pi to the power of n by 2. N is equal to 2, but let me just write it anyway. Then determinant of sigma to the power of half. Okay. E power minus half x minus mu. So mu is 0. Okay. So mu is 0, 0. Okay. So this mu will not come. Sorry, 0, 0. So let's, we don't have to take the subtraction. Okay. So let me just clear this. So this will be x transpose sigma x. Okay, you may be thinking, why are we dealing with this extremely complicated multivariate Gaussian, which has so many things of linear algebra and then what not, and without looking at any applications. Okay, so let me just remind you, this is a very, very popular class of algorithms. Okay, so this will be used in places like when you do deep learning, you will have you will see what is called as radial basis functions. Okay, you will have something called as mixtures of Gaussians. Okay, so this is like an extremely important class of algorithms. Okay, then there is things called as Brownian motion. Okay, Brownian motions. Okay, or Wiener process. So these are all very, very important class of algorithms. There is, in general, it goes to the random processes. Okay, and that leads to Gaussian process. Okay, it has fantastic applications in stochastic finance, machine learning, and you know, if you go deeper and deeper, you will find that this multivariate Gaussian is extremely useful. Okay, so it may be sounding like very dry, dull algebraic exercise, but please bear with me. All right. So coming back to the issue at hand, what we have is x is a multivariate Gaussian, x1, x2, whose distribution is, assume I have taken the example that mu is 0 and variance is sigma. All right. And then y is equal to ax plus b and x is equal to a inverse y minus b. And then we have the multivariate probability density function as follows. Okay. So up until this point, are there any questions from the class? So for those of you who are a bit rusty in linear algebra, this might be a little difficult. Please mail me if you have any questions, if you need any additional help. Okay, it is my duty to help you. So if you have any questions, please let me know. I will try to do whatever possible to help you here. Okay. So, but on this general setup, is this okay so far? Shall we continue? Okay. So I will, yeah, thanks. So let me just make some space. Okay, so so in your exam, I'm not going to ask you very difficult questions here. The point is not to, make you get zero. That is not the idea. The idea is I want you to learn like the key takeaways which will help you when you go to the next semester. Okay. So that's the whole idea. I'm not going to set you questions which are difficult. That is really not the aim. Even if you felt like the midterm exams were particularly difficult or the assignments are particularly difficult, that's not the idea. It is just that you learn around that concept. Okay. So it's not that I am choosing the most difficult question to give. That's not the idea. Okay. I just want to be clear here. So yeah, anyway, so I will ask simple questions around this in the exam, if at all. Okay, so, but yeah, not to worry. So this can get very complicated. Okay, the point is not to test your calculus level knowledge. That's really not what it is about. Okay, so now we are here. So now let's try to basically first, in order to really start applying this formula, we have to have H. So H is ready, right? This is H. This is G and this is H. So let me write in brackets. So this is like G and this is H. So H is ready. So what we need is the Jacobian matrix. Okay. So now the beauty of this thing. So what is that? Jacobian is JH of Y, right? So basically I'm taking the derivative of H with respect to Y. So when I take the derivative, if this Y was a linear, suppose this was a single variable case, what would the derivative be? If Y was a single random variable, what would be the derivative be?
1 by
1 by A or A inverse, right? So the same thing holds even here. You can try it out. Okay. I don't know why this is happening. All right. So let me see. Right. Okay. Oh my God. Ah, okay. Let's see. So this is G. Someone has any question? What is that? All right. Don't know what is happening. Okay. All right. So this is this. Okay. So this is G. This is H. Okay. So now JH of Y. Okay. It is going to be very similar to how if it was linear. So this is going to be the A inverse matrix. Okay. So you can, how do you check this? So what you need to do if you want to check this is suppose A inverse is given by B11, B12, B21, B22. Suppose A inverse is given by this. What you can do is you can write basically x1, x2. You can write it as uh, A inverse. So this matrix into y1 by 2. Okay. So this matrix, which is B11, B12, B21, B22. Okay. Into the matrix. What is the matrix? Y1 minus B1 and Y2 minus B2. You take the multiplication of this matrix. Okay. So you will get some function here. And then when you take the partial derivatives in this way, okay, with respect to y1 and y2, when you take that, you will get that uh, the matrix, the Jacobian matrix is A inverse. Okay, so I will let you do this. So this is a homework for you. Maybe I will give you to do as part of your, let me just make a note of it, part of your assignment. Okay, so let me just clear this off. So we know what is this. So now we are ready to apply the formula. So let's do that. So F y1, y2, yn of y1, y2, yn is so so the determinant of this one comes, right? So the Jacobian determinant. So basically that will be here will be okay. What's happening? Okay, let me just save this. November. Okay, so here there will be determinant of A inverse comes. Okay, so that is the Jacobian part. And then we have to start writing in terms of y minus b. Wherever x comes, we have to write A inverse y minus b. Okay, so let me do that. So I will just keep this in for your reference so that you can see what I'm doing. So this will be 1 over 2 pi to the power of n by 2. Okay, this then you will have determinant of I'm just having some strange problems. Okay, so this will be determinant of just a minute, guys. Let me just reconnect my device. Hopefully, this should fix it. Determinant of sigma. Okay, let me try to reduce my memory usage. Maybe this is something this person cannot manage. Let's try once again. So this will be 1 over 2 pi to the power of n by 2 determinant of sigma to the power of half. Okay. Now wherever x comes, I am going to replace it by A inverse. Okay, so this will be minus half A inverse y minus b transpose sigma inverse y minus b. Okay, so that's how you get the transform. Okay, now what you can show, okay, so if you rearrange the terms and okay, and do the manipulations, what you will get is that y is distributed as, yes, people know this, right? I have taught you already if a and x are multivariate, how the mean will shift. So mean is easy, right? The mean will be a b because you can see that there is a b component. Okay, what I'm omitting now because somehow my pen is acting up. So what I'm going to do is I will write this as A sigma A transpose. The variance now changes to A sigma A transpose. The covariance matrix becomes this. Okay, so you can do some rearrangement. What you can do is this particular thing, right? Determinant of A inverse. This is equal to 1 over determinant of A. Okay, and then what you can show is that this is 1 over determinant of A transpose into determinant of A to the power of half. You can do all these things. Okay, and then you can bring these components here, and then you can do some algebraic manipulation to show this. Okay, so I'm skipping this for now, but I hope the idea is clear. Are there any questions? I need some response because this is a kind of a difficult topic. Yes, people, are there any questions? Everything clear? Am I online? Nikhil, what is not clear? Please ask.
Hello, sir.
Yeah,
Uh, Sir, in this last equation,
yeah,
uh,
yeah.
I think we have missed one A inverse. It should be like X
Yes,
transpose
yes,
sigma
yes, yes, yes. Here there is a A inverse. I'm
A
sorry.
inverse. Sir, in the equation above that, wherein we have found Fx, the
This
PD
is
of 2x.
yeah.
Yeah. Sir, in that, is it sigma inverse? Sigma inverse?
Yes, yes. I'm sorry. So these are all the kind of mistakes I do. But this is I'm so sorry. Yeah, but it is there. But thanks for pointing out. Anything else, people? So last somebody wanted me to explain the last part. No question. Okay. So Aditya wanted me to explain the last part. So basically, let me just give a quick recap of whatever we did. Okay. So what you have is like you have X whose density you know. Okay. And the density, since I've taken zero, mean and variance as covariance matrix as sigma. Okay. So we know the density. Okay. And then what we do is we know the density, we have written the density. Okay, so this is what is the density. Now, in the multivariate case, when you know the density of x, if you want to find density of y, where y is some function of x, what you do is first thing first, you replace wherever x comes in as a function of y, right? So that is what we did first. So that's what we did here. So y was replaced by, so x was replaced as y minus b into a inverse. Sorry, a inverse into y minus b. So that's what we got here. Okay, so there is a inverse here as Ramnath pointed out. Okay, and then there is a second part which is the Jacobian. Okay, so the Jacobian, if you take, I haven't explained you the details, but if you take A inverse as some matrix and if you take the partial derivatives and you write it, you will confirm that the Jacobian of x with respect to y in this case, okay, jh of y will be actually A inverse. So the determinant of that Jacobian will be determinant of whatever A inverse matrix is there. Okay, so then we put this. Okay, and then this is a identity. Okay, so this is a linear algebra identity. Determinant of A into determinant of A inverse. What is happening? Determinant of A inverse. Okay, this is equal to 1. Okay, so then we can actually replace determinant of A as 1 over determinant of, but determinant of A inverse as 1 over determinant of A. Okay, then there is one more identity. Determinant of A is equal to determinant of A transpose. This is one more identity. Okay, so then what you can do is like determinant of A inverse. So A is basically, I can write this as determinant of A squared to the power of half. Okay, and the first, there are two determinant A, right? The first one I will write it as determinant of A transpose, and the second one I will write as it is. Okay, the purpose of doing this is then I can merge. So there is a another identity which is determinant of product of two, this one A into B, two matrices, is equal to determinant of A. I'm sorry, the pen is behaving very strange. Determinant of A into determinant of B. Okay, so this you can show. And using this identity, we merge it and then we rearrange such that it starts resembling the standard normal. And that will show us that y is now also normal with mean b. Why is it not mu plus b? Because mu is chosen as 0. Okay, so that's how this comes. Is this fine, Aditya? All right. So any other questions? Okay. So let's do one more example, and then we will move to convolution. So example 2. Okay. So let's say x. Oh my God, what is this? Something has broken in my device. Okay. So example 2. Does anyone know what could be happening? Let me turn off. Yeah, let's see. This might help. Okay, good. So example 2, what we will do is like we will take the same x, okay, normal, 0, and uh, sigma, we will take it as identity. Okay, so let's take this. Now, this is the thing. So let's say x is basically x1, x2. Okay, so it's a bivariate Gaussian. So what is this? It's a bivariate Gaussian. Now what we will do is we will we will define R, which is equal to x1 square plus x2 square. This is R. Okay, and then I will define theta, which is tan inverse x2 by x1. See, basically I'm doing the conversion from x1, x2 to polar coordinates. Okay, but instead of taking the radius, I'm taking radius square. Okay, so this is the first function. But if you want to write it other way, x1 is square root r cos theta, and x2 is square root r sin theta. Okay, so now r is a value which goes from 0 to infinity. Okay, and theta goes from 0 to 2 pi. So let me draw this. What you have is x1, x2, okay, and this is, I'm calling it as square root of r. This is my theta. Okay, so this is the change that I'm doing. Okay, so I hope this is clear to everybody. So now if I want to write, so everything is done. So we can now actually do fy of y1, y2. Oh, sorry, it's not a y anymore, right? So what is this? Okay, so this is fr theta of r and theta, right? That's what we want to do. That is nothing but f of x1, x2 of h1 of r theta, okay, h2 of r theta, okay, then Jacobian of h with respect to r theta, determinant of this matrix and its uh, absolute value. Is this okay? So let us do that. So what is the density for a bivariate x1? And I really don't know what's happening, but anyway, let's push on. So let me just delete this. So don't know what is this. Okay, anyway. I don't know what to do this when this happens.
Sir, is there a kind of a button on the stylus that you're using?
It is there, but is that pressed? Is that what you're thinking?
Yes, yeah. So sometimes it happens like, I mean, if it
Yeah.
gets pressed.
Yeah, maybe I'll just try to experiment with it. I think the stylus is broken. I mean, too many classes, too many videos. Just a minute, guys. So let's see if I will try to clean up some of these things and then see. All right. Maybe I should use my pen to like mouse to write. Let's see. So f of x1, x2. This is 1 over 2 pi to the power of n by 2, which is 2 pi, e power minus half. Okay, I will write simple. I will write it as x1 squared plus x2 squared. Okay, so this is what it is, x1 squared plus x2 squared. Now I will replace yeah, so now we are ready to apply the formula, right? So this we see. So what is this going to be? So I'm going to apply square root r cos theta here. So what is square of this? It is r cos square theta plus r sin square theta here. Okay. So r cos square theta plus r sin square theta, r cos square theta plus r sin square theta. This is going to be r. Okay. So what we will have? We will have 1 over I think you're right. Some button has got pressed somewhere. All right. So I will figure it out later. Okay. So what is this going to be? So this will be 1 over 2 pi. Okay. The first thing, and e power minus half r. Okay. Because this whole thing simplifies to r. So e power minus half r. Okay. So now we have to find out the Jacobian of this with respect to r theta. So J H matrix we need to figure out. What is this? So it's taking the derivative of this one first with respect to r and then with respect to theta. So when you take the derivative of this with respect to r, you will get 1 over 2 square root of r. 1 over 2 square root of r. This will be cos theta as it is. The other one will give you minus square root of r sin theta. Okay, and here it will be the same way, 1 over 2 square root of r. Okay, this will be first I'm taking the derivative of the second component. Okay, x2 with respect to r and theta. The first one is with respect to r, and then here it will be plus. There is no negative. The previous one had negative. This will be square root of r cos theta. Okay. So here there is a negative. Let me just make it predominant. So what is the determinant? So if you take the determinant, you are going to multiply this and this square root of r, this square root of r goes, this square root of r, this square root of r goes. There is a half common. Okay, so the determinant of this, determinant of GH is going to be half. Okay, so you will get a half here. Fine. So you will have 1 over 2 pi e power minus half into half. Okay. So now what is this? This whole thing. Yes. Anyone? What is this? This is a completely a function of r. So what does this remind you of? Anybody?
Exponential distribution.
Yes. So this is an exponential distribution with lambda half. What about this? 1 over 2 pi. See, look at the range of theta. It goes from 0 to 2 pi. If I say it is 1 over 2 pi, what is this going to do? Anybody?
Mean or expectation, maybe.
So this is uniform. This is uniform between 0 to 2 pi. Okay, so this is the density of uniform for theta, and this is the density of exponential. Is that okay? Whoever answered, do you follow what I'm trying to say?
Yes, sir.
So this is so now basically R and theta are independent. They are separated out, and one is uniform, other is exponential. Okay, so these two examples I wanted to give. So I hope the topic of derived distribution is clear to everybody. Any questions so far? I don't know how I will do for another 20 minutes, but let me just pause and ask if there are any questions. Aditya, is everything okay now? How about everybody? Is everything clear? Can I have a quick poll? Everything clear? Okay. Ramnath, everything fine?
Yes, sir. Yes, sir.
Okay, so this finishes derived distribution. So next I want to talk about convolution, if the stylus permits. So let us see. So let me do one thing. I will just start the MIT lectures harder to follow. I will also make my own versions of those MIT lectures. Okay, but that will take some time. All right. So right now, because of this stylus issue, I'm going to stop here a little bit earlier. Okay. So, are there any questions? If there are any questions, I will take up now. I understand that I have not even gotten into convolution, but it's too difficult, believe me. So I will just make a associated video for this. Okay. So I think it's a good time to stop here. So if there are no questions, then we will stop. All right, so we will stop here. Thank you very much, and have a good lunch. Thanks, guys.